Why is this construction of the regular pentagon with ruler and compass, starting with its side, the simplest and the most accurate and the best construction we can have? I'm going to show you now the rationale behind this construction. We have made an auxiliary construction below the pentagon, which was a perpendicular line and taking half of the side and then half of the side again. Let's start explaining why we have done this. Let's call the side of the regular pentagon length 1 in order to make things easier. Then we can generalize to any side, to any length. So AB is 1. BP is 1/2 because we took half of the side. And then again, PQ is also 1/2. So we have a right angle triangle here. We can apply the most famous theorem in math, which is Pythagoras. And we can calculate the side of AP, the size of AP. So AP squared is equal to 1 square, 1/2 square, plus 1 square. The order of the sum doesn't make any change. AP square is 1/4 plus 1, which is 5/4. Taking square root, AP is square root of 5 divided by 2. That's the length of AP. But then we have to add 1/2. So AQ is 1/2 plus square root of 5 divided by 2. So we can have here common denominator 2, and we have 1 plus square root of 5 divided by 2. This number is famous and it's called the golden number. We have derived that in the auxiliary construction, AQ is 1 plus square root of 5 divided by 2, which is the golden number. What has to do that number with the regular pentagon? We are going to demonstrate that that is exactly the length of the diagonal of the regular pentagon. That's what we are going to demonstrate. So first, we are going to figure out what's the measure of each angle of the pentagon. A, B, C, D, E. We draw two diagonals in the pentagon, AD and BD. Okay, we have two diagonals. So the angles of the sum of the angles of a triangle is 180 degrees. Here is the same case. We have a triangle 180 degrees and 180 degrees. So the pentagon is formed by 3 triangles. So the sum of the 5 angles of the pentagon, A plus B plus C plus D plus E, is equal to 180 multiplied by 3, which is equal to 540 degrees. Okay, but the 5 angles of the pentagon, since the pentagon is regular, are equal. So we can substitute B, C, D, and E by A. So we have 5 times A equal 540. So if we find out what is A, is 540 divided by 5, which gives us 108. And that's the angle of the regular pentagon, the inner angle of the regular pentagon. So we have here that this is 108. This one similarly is 108. And also this one, and this one, and this one. All the 5 of us are 108. Okay. But we have here, we are going to continue to deduce the angles that are inside here. This is an isosceles triangle, AD. So these two angles need to be equal. How can we calculate AED? EAD, sorry, is 180 minus 108 divided by 2. This is 72 divided by 2, which is equal to 36 degrees. So this angle is 36 degrees, this one angle is 36 degrees, and similarly this one is 36 degrees, and this one is 36 degrees. Well, we still have to find out the angles of this one. If all these angles 108, ADB is 108, which is the whole angle, minus 2 times 36, and that's equal to 36 degrees, which will be this angle here. And we need to calculate this angle. We're going to put it in green, 36. This is the angle of the star. 36 degrees is the angle of the star, of the 5-point star. If we draw all the diagonals, you remember that we have the same. And so this one, the last angles that we have here, DAB, is 108 minus 36, which leaves us with 72. And similarly, this other angle is 72. This angle is 72, and this angle is 72. Okay. Well, we have found out the angles of the regular pentagon and the angles of the point of the star. All the angles that are involved there. We have to now to find where the golden number appears here. We have deduced the angles of the pentagon and the star, and we have drawn this diagonal, which is the angle bisector of this angle. As you see here, 36, 36, 36. Here is 36, 36, and this will be 36. So we are going to work with the central triangle ABD. And so we have that this angle is 36, and this angle is 36. Well, if this angle is 36 and this angle is 36, we can deduce that this is 108. And so if this is 180 minus 108, this is going to be 72. So we have here two triangles which are similar because they have the same angles. ABD is 36, 72, 72. And ABGJ is also 36, 72, 72. And we know that similar triangles, their sides are proportional by the Thales theorem. So, basing in that famous and very important property, we are going to deduce the length of AD. We started setting that AB is 1. And then, since ABJ is isosceles, this side also has to be 1. Let's put X, the unknown, which is the diagonal. Since AJD is isosceles, this side has to be equal to this side, so DJ is 1. But all this BD is X. So if this is X and this is 1, BJ is X minus 1. Okay, well, we write that ABD is similar to ABJ. So, by Thales, let's write Thales, proportionally, sides, AD divided by AB is equal to AB divided by BJ. In terms of the unknowns we have is X divided by 1 is equal to 1 divided by X minus 1. We do cross products and X times X minus 1 is equal 1, which leads us to the second degree equation x squared minus x minus 1 equal 0. So we solve this equation as is 1 plus minus square root of 1 plus 4 divided by 2. So we have two roots here, is 1 plus square root of 5 divided by 2, or 1 minus square root of 5 divided by 2. We dismiss this one because it's negative, and the length of a side cannot be a negative number, and so we stay with this one, which is the golden number again. The famous golden number that is all around in math, in art, in biology, everything. And this is approximately, with 3 decimal digits, 1,619. So we can deduce now that exactly the diagonal of a regular pentagon of side 1 is the golden number, which we have constructed by the Pythagoras theorem. Well, this is a pentagon with side 1. If we want to generalize, let's say this is not 1, it's side S. We have deduced that if the regular pentagon has a side of 1 equal 1, length 1, so the diagonal is the golden number, 1 plus square root of 5 divided by 2. But if we want to generalize, let's say we have a bigger or a smaller pentagon, of side S. So since the pentagons are similar, if we have to multiply 1 by S to arrive to the side, we have to do the same thing for the diagonal. So the diagonal of this pentagon is going to be the golden number 1 plus square root of 5 divided by 2 times S. In the same way, we identify square root of 2 as the diagonal of a square, we can identify the golden number, the famous golden number, as the diagonal of a one-side regular pentagon. And if we divide the diagonal into the side, the diagonal is 1 plus square root of 5 divided by 2 times S. Divided by S, we cancel and we get that the diagonal divided by side is the golden number, which is approximately 1.618. That's the golden number. There are many stories about the golden number, but the point where its birth, its origin, is the ratio between the diagonal and the side in any regular pentagon is the famous and beautiful golden number.